Okay, now today we're going to actually write our first machine language program. Now, last time we went over the concept of the von Neumann cycle, and what are the steps of the von Neumann cycle? Have you memorized it yet? What's the first one? Fetch, decode, increment, execute, and repeat. Fetch, decode, increment, execute, repeat. Boom, 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 boom. Over and over and over again, a billion cycles plus per second. That is the von Neumann cycle. And what do we fetch? What are we fetching?
Instruction.
An instruction. How do we know where to go to fetch it? The program counter, yes. The program counter has the address of where to go to fetch the instruction. We decode it by looking up in the table. The electronics does that. We increment the program counter. Why do we increment the program counter? Because we want it to point to the next instruction. So they are stored sequentially in memory. And then execute the instruction and then repeat. Now, so here's our our first machine language program is going to use these instructions. The load byte instruction. And so here is the load byte instruction. The example that we gave in figure 4.24 and 4.25 is D1004A. So do you see, if you look up for the D, the opcode is 1101, and that is the load byte instruction. Okay, and then register R is 0, so that indicates the accumulator. And then 001 is the addressing AAA field. Yeah. And the D1 is the instruction specifier, and the 004A is the operand specifier. Are you with me? And the operand specifier, with direct addressing, the operand specifier is the address in memory of where you go to load the byte. Now, is that clear? So that's load, and then we did this example with load byte and accumulator. And then the other one that we're going to do is store byte. So the store byte has instruction specifier 1111, register field R, and then addressing field AAA. And the example that we looked at in figure 4.26 was F1004A. Yeah? And then we looked at how we can, in figure 4.28, we looked at how we can store a byte to the output device. And so what happens is, if before the instruction executes, you have the bits for an ASCII character in the right half of the accumulator, and you store that to FC16, that's where the screen is, and so once it goes to FC16, it goes to the output stream. All right, so here we go. Let's do it. Oops. Now, so in figure 4.33, here is our first machine language program. And we have in the top part of the slide, we have it all written out in binary. Now, and we've talked about how this looks visually on the printed page or on the screen, right? That the address in hex is on the first column, which is on the left, and then the content of main memory is on the right. And we have two different versions here, a machine language and in binary, and then the other version is a machine language in hex. Does everybody understand how to read this code, this machine language code? Notice that the first instruction in the machine language hex version is D1000D. And D1, we just saw in the previous slide, is what? Load byte accumulator. Does everybody see? And so what is this going to do? It's going to load byte, and where is it going to go to get that byte? What address? 000D. Now look, what is at 000D? Do you see how to count that? You see how to count those addresses down? You know, 0000, and then why is the second address 0003? Because there's 3 bytes on the first line. Does everybody see? And then, is everybody clear? And then 0006 oh, sorry, 0003, what is that instruction? F1, what is the F1 instruction? Store byte accumulator. And where is it storing it to? FC16. Now what is that FC16? The what? The output. This is memory mapped input output. Is everybody clear? Okay. And then what's the next instruction? D1000E. So what does that do? That's another load byte accumulator. Does everybody understand how to decode the D1 with the opcode? And okay, we went through all of these skills for decoding and looking up the tables. Okay, so D1000E load byte accumulator to the I, and then the next one is F1 FC16 again, and what is that? Store byte accumulator to the output device. And then after that instruction executes, we need to have the program stop. So that's the 00 instruction. Now is everybody clear on that? Yeah.
Is there some sort of like start program byte also?
Yeah, that's a good question. How did things start? So that is in the PEP9 virtual computer, we just run one job to its completion. And then once we finish, and once stop executes, we return back to the app. And then whatever you do in the app determines, what the next state of the computer is going to be.
It knows where the start of whatever you're trying to do is.
Ah, that's a good question. Oh, yeah, that's a good question. In a real system, when an app terminates, it got called by the operating system. So in a real physical system, the operating system takes over when the program finishes execution. So in a real system, this wouldn't be stop. This would be return to the operating system.
But the operating system knew to go to byte 0000
Oh.
instead of starting at byte 0000.
Oh, that is such a good question. In PEP9, this is a very simplified version. In the PEP9 virtual machine, the system assumes that the program is loaded starting at address 0000. That is way unrealistic. In a real system, jobs are all over the place, and there has to be a way to set the program counter to the first instruction of the job, and it's not necessarily 0000. That was a really good question. So yeah, you see, look, I mean, these are the kinds of details that you have to worry about if we had to, all of this. I mean, it's just, there'd be a bazillion different details, and yeah. So anyway, that's a good question, though. So everybody understand that with the PEP9 virtual machine, we assume that they're being loaded starting at 0000. Is everybody good? So now look at this, you guys. After the stop instruction, what do we have? We have 48, which is the ASCII code for the letter H, and 69, which is the ASCII code for the letter I. So what do you notice is happening in this program? What is the address of the letter H? 000D. And you notice that is in memory at some memory location. But look, what is that memory location 0009? F1. But is that data? Is that F1 to be interpreted as data?
It's a command.
It's a command, it's an instruction. So notice that main memory is storing not only the program, but also the data. Not only the data, but also the program. Main memory stores both. Both are binary. Now that is super important. That is part of this von Neumann design. That's what the von Neumann cycle, how the von Neumann cycle operates. It assumes that the same memory is storing both programs and data. Now that is super important. So everybody see that that's an inherent part of the von Neumann design. Are you with me? Is everybody clear? Now let's take a look. Let's run through this program. Let's see how this program executes with each individual step of the von Neumann cycle. So that's the program. Now let's take a look. Here in figure 4.34a. This is the initial state of the PEP9 computer before loading. Now, we've left off the disk. We've left off some of the registers in the CPU. We're only showing a little small part of the main memory. Is everybody clear? In part A? So now before the von Neumann cycle can start, what has to happen? You remember that? Before we do fetch, decode, we can't start fetch, decode, increment, execute, repeat yet. What has to happen first?
Load the machine language.
The machine language, yeah, that program has to be stored in memory, starting at address 0000. Now, does everybody see part B? What has happened? Do you recognize that D1000D in memory? That's the first instruction of our program. Is everybody clear?
Which one?
In figure 4.34 part B, you see at mem sub 0000, the content is D1000D. So if you go back here, that is the first instruction of the program. Is everybody, are we good? So it's the function of the operating system loader to do this. That has to happen before you start the von Neumann cycle to execute the program. Is everybody clear? That's a separate step outside this. So that has to happen somehow. The program and all of its data, associated data, has to get into main memory somehow. It might be on disk. You know, you have an app on disk. You want to run a program. It's going from disk to memory. It has to be installed in memory before it can be executed. Is everybody good? Okay, so the program is loaded into main memory. Okay, so now what? So now what's the first step of the von Neumann cycle? Oh, and what about the program counter? There's one more thing that has to happen. Now what do we have to do with the program counter before we start the execution cycle? Yeah, it has to be initialized. So here in part C of the figure, the program counter is initialized to 0000. Now why is that? Because we assume the what? The program is loaded starting at 0000. Now, is everybody clear on that? This all literally happens in these machines. This literally is, there is a program counter. And it does this, it works like this. Okay, now we can start the execution cycle. Now what's the first part? Fetch. Now what do you suppose we're going to fetch? Exactly, we're going to fetch the instruction at 0000. And where do you suppose we're going to put it? No, we're not going to put it in the accumulator, no. Yes, what does IR stand for? Instruction register. So here, do you see in part D, we have fetched the D1000D into the instruction register. Now, so it has to go from memory over the bus into the IR. Now, is that clear? See how nice and visual this is? Okay. So that's fetch. Now, what was the second step? Decode. So, you know, we're not going to show the state, what happens in the decode.
Would there be, is it just now being shown, or would there be a control being sent from the CPU to fetch the...
Yeah, the control lines I'm not bothering to show. Right. And also, this doesn't happen in just one step. It fetched the instruction specifier, it decoded it, figured out that it was a non-unary instruction, so it had to fetch the other two. You know, so all that happened in this, we're showing that in just one step here. But that's a lower level of abstraction, that's more detailed.
Okay.
Yeah. Is everybody good? So that's fetch, decode. And now what's the next? Fetch, decode?
Translate.
No. Increment. What do we increment? The program counter. By how much in this case? 3 altogether.
3 bytes.
Because it fetched 3 bytes.
Oh, so it already decided that code D1 was something that required 2 extra things.
Yes, that's a lower level of abstraction, and I'm not showing those separate steps, but they would be separate. They are separate steps literally in the hardware. Are we good? So what is the state going to look like? What will the program counter be?
0003.
Boom, 0003 is right. All right. We're thinking like machines now. It's all very mechanical. Okay? And now fetch, decode, increment, now what? Execute. Now what instruction is executing? D1000D. So what instruction was that?
Load byte into.
Load byte into the accumulator. From where? Yeah, and what address in main memory? 000D. And what is there in 000D? What's there?
H.
Well, no, in hex, what is it? It's 4.8, right? So there's puts it in the right half of the accumulator. Is everybody good? In part F. Are we good? Now what? So that was execute. So fetch, decode, increment, execute, repeat. So repeat. What's the next? Fetch. But now what's the value of the program counter?
F1
Well, no, the value of the program counter itself. 0003. So it goes to 0003, address 0003, and fetches it. And what is it? What is at address 0003? F1, FC1, 6. You're right. So what happens? That's going to go into the where? Into the IR. So does everybody see in part G? Are we good? This literally physically happens. I'm not making this up. This is happening on our computers as we speak. Okay, so fetch. What was the next? Decode, we don't show that. What's the next? Increment, what happens to the program counter? Exactly, goes to 006, as shown in part H. And now, execute F1, FC16. Well, what is the F1 instruction? Store byte from the accumulator to FC16, but FC16 is the what? Is the output. So what happens?
It gets stored.
Boom. There comes the H. Now, is that clear? Yeah.
Is the accumulator always for?
Oh, that's a good question. The accumulator is 16 bits, it's 2 bytes, and it can be represented by 4 hexadecimal digits. And there is always something in there.
It's always that many.
It's always that many. Oh, absolutely. These registers are fixed. That's a really good point. These registers are fixed in size. When you manufacture the chip, that's set in the hardware. Yeah, there's no expanding here. Yeah, oh, that was, yeah, that's a good point.
And is you said 2 bytes?
This is always 2 bytes. Now, in a real computer system, they're not this tiny. This is a super tiny example. We're going to see a real machine. We're going to see the registers in a real machine here a little bit later. But is everybody good? Okay. So okay, and now what? Fetch, decode, increment, execute what?
Fetch.
Repeat, which you don't show, and then fetch. So we'll fetch what? Yeah, D1000E. Decode, increment, what? Yeah, I think this is the last one, though. Oh, no. Oh, wait, increment. We had the increment, right? Increment. And then what? Execute. Now, what's the D1000E? That's the load byte accumulator. So what, from where? 000D. So what happens to the accumulator? Instead of being 0048, what is it? 0069, and I think, et cetera, et cetera. Now, does everybody see? And then it will go through, and the I will come out, and then and by the way, the program counter will get incremented to what? 000C, right? And then it will execute, and then it will fetch the stop instruction. The program counter will be incremented to what? 000D, but then when the stop instruction executes, that's when we return to the simulator, to the app, the virtual machine app. Is everybody clear on how that works? Okay. Now, here's what we're going to do now. Now we're going to demo how this actually works on the PEP9. Now, I've talked to a few students who have downloaded the app. Did you see the link on the web page and go to computersystemsbook.com and do the 5th edition and get the PEP9 app? So, any questions about that? Let me demo it for you. We're going to have to remember this program. So what is it? Now, in order to run this on the simulator, we have to write a machine language program, we have to write it in hex. We write it in hex. But what we have to do is we have to tack on an extra lowercase zz to tell the loader where to stop loading. So this lowercase zz is going to be a sentinel for the loader. So now what let's do is let's do a demo and see how this actually works with PEP9. Okay, so here's our PEP9 app. Now, for these machine language programs that we write from scratch in machine language, we're going to put the machine language program right here in this object code pane. But before we do that, there's one thing we should do. Up here, the default for the app is to show the code and the CPU. But for these machine language programs, it's helpful to see not only that, but to see the code and the CPU and main memory. So if you click this little icon, the memory dump pane shows up over here. And you see that you see how to read the memory dump? This is 00, this is at address 0, 1, 2, 3, 4, 5, 6, 7, and this is 8, 9, 10, etc. And these little dots over here, what happens is when you put stuff in memory, these little dots, if it is a printable ASCII character, the ASCII character representation will come up on those little dots. This is really standard. This is just the standard memory dump format. Okay, so now we have to read off we have to enter our program. So what was our program? Somebody tell me.
D1.
D1. Now be very. Oops. Hold on. So D1. Now it's really important. Exactly one space, and then what?
0, 0. 0D.
0D. Now here's another important thing. We could do a space and continue it all on the same line if we wanted to, or we could put it on a separate line if we want. But if you put it on a separate line, you cannot have a trailing space. You have to have exactly one character, whether it's the trailing space or the new line character. Sorry, whether it's a space or no space, but instead the new line character. Now, is everybody clear on that? So here, it would be wrong to do this. Space return. The loader will not function. It's a very picky loader. So here. Okay, what was the next instruction?
F1.
F1.
FC.
FC. Oops. One space. FC. 16.
D1.
D1.
0, 0.
0, 0.
0E.
0E.
F1.
F1.
FC.
FC.
16.
16.
0, 0.
0, 0. And now that's the stop instruction, right?
Yes.
So now what were those two?
48.
48. Space.
69.
69. Now it's space, lowercase zz. Now is everybody clear on that? How to do that? So now, you guys, we can run it. Here's the input, here's the output. This program has no input. So if we've done everything correctly and we come up here to run, okay, so what we have to do in order to run this program is we have to go to build and we have to do run object. Okay, you have to go to build and run. But before we do this, when you do run object, what happens is that does two things. What that does is it puts this program into main memory and then it runs it. Does everybody see what we're saying? So watch here, when we go up here and do build run object, watch what happens. Boom. Now did you see what happened? Look, here's first in the memory, it loaded D1, 0, 0, 0D, F1, FC, 1, 6, D1, 0, 0, 0E, F1, FC. Does everybody see how that worked? And what came out? Hi, it worked. Now, there's another really slick feature, though, with this app, and that is, what we'll do now is let's first go to System and Clear Memory. Okay, so now notice that it cleared off everything here, and the memory dump is all cleared out. And now what we're going to do is we are going to see how each one of these instructions works individually. Now watch this. Now we go to Build, and we do Start Debugging Object. And when we do Start Debugging Object, watch what happens. Now you see, look, what did it do? It loaded the program into main memory, starting at 0000, and it set the program counter to what? 0000. Look, here's a little CPU. You see the NZVC bits, the accumulator index register, blah, blah, blah. Yeah?
The preparatory, like 0x,
Oh,
like a indication that it's hex.
yes, that is the industry standard. Yeah, the initial 0x means a hexadecimal value. Yeah, and in fact, those of you who are in data structures remember that from when we did the hash table stuff, we did 0x for hex values. Yeah. Question?
What did you run just right now?
Oh, I did, what I did was build, start debugging object, okay? All right, and now not only this, but here, look, it gives us the ability, it enables this single step button. Now look, you guys, what is the value of the program counter? 000. And what is highlighted here? The instruction at 0000. So when I click this single step, what's going to happen? This instruction will execute. Are you with me? The program counter will be incremented. And what will be in the accumulator?
0003.
What will be in the accumulator? Say it again. 48 on the right half of the accumulator. So watch here. Boom! There's the 48. And the program counter got incremented to 0003. And this is going to be the instruction to execute next. Is that slick? Yeah.
What does the memory dump to the right of it, what does it mean when it has those symbols?
Yeah, see, look, do you see this 48? That's the H, and the 69, that's the I. If there's any content in the memory dump that is a printable ASCII character, then that ASCII character gets printed out on that little right-hand side. But they're not all printable. They're not all, you know, if you were to interpret, you know, those as ASCII characters, that's what they would be. And you can see that the ones that we want to be interpreted as HI, they're right there. Is that, and this is, by the way, this is way standard. This is the standard memory dump format. You'll see, if you ever have to deal with coding at this level and you have to go in and interpret memory dumps, which, by the way, people do all the time who deal with viruses and security issues, and they have to go and they have to figure out what's going on in memory, you know. Yeah, Garrett?
Here is that.
That's the letter H and that's the letter I. So look, the 48 is here, right? So now let's do this. Now what does this F1, FC16 do? Yeah, it sends it to the output. So here, single step, boom, there's the H. And so now the program counter got incremented to 006, and now the next instruction to be executed is going to be D1000E. Yeah.
Is FC16 like the output area for the PEP9, like PEP9 knows that's the output area, or?
That is a good question, and the answer is yes. That is reserved. The operating system or the heart, that is installed there. It's like it's in the for PEP9. Oh yeah, all of this stuff is all specific to this virtual machine. Yeah, so we would have to know that is where the output is wired into. Yeah, question?
Is the first?
That's 0E.
Okay.
Look, that is the second byte of the operand specifier. The instruction is D1000E, like that. Why that's breaks on the line? Well, look, inside the computer there are no lines. It's all electronic. Putting an instruction on a single line is for human consumption. It's for our human understanding. But literally what happens is those are electronic signals in main memory. And so they just go sequentially in main memory. Are you with me on that? That was a good question. You see the difference between, yeah? Is everybody clear? Okay, so now what's going to happen? What's D1000E going to do? Get the I and put it where? In the accumulator. So now there's the 69 in the accumulator. And now what's going to happen? Output. So boom, there goes the I. And now notice that what happened was the program counter is now at 000C. So what's going to happen next?
Stop the instruction.
Yeah, so we will fetch the stop instruction. So there, notice that it says the instruction specifier there in binary, okay? And now, we're still running, now what's going to happen? Oh, sorry, we executed the stop instruction, so boom, so now we're back. Now there's one other little handy feature here that you guys might like. This is a little byte calculator up here. Look, this is in decimal. If you make this 98, then that is hex 62 and it's binary 01100 and the letter is B. And here, if you want the letter, you can, any one, capital Y, there's the binary, there's the hex, there's the decimal. You can do any of these fields.
Is the hexadecimal just on the right? Yeah.
And this,
That's all this one.
and binary, look, you can even do it in binary. Let's change this to a 10. Oh wait, I didn't do it. To a 10. So there's Z. See? And what's the difference between that and a lowercase z? What's the difference between that and a lowercase z? See, that's this. Pretty slick, huh? Somebody had to program that for you. All right, does everybody see how that worked? Okay, good deal. Yeah, question?
Two quick little things. On the hex thing on that calculator, why is it a 0x and then like...
0x is an indication that the quantity that follows is a hexadecimal quantity.
Okay.
That is a standard programmatic way to indicate hexadecimal values in all the C languages, like in C, C++, Java.
Okay. And then on the PEP9 part for the source code window, we don't really...
Well, not yet.
Right. Okay.
We're programming in machine language.
Okay.
Yeah, that's coming up later. Because we are at level ISA 3, what level is that going to be?
Maybe 2 or...
No, 2 was HOL 6. That's like Java and C. What's the one just below that? A little review of the levels. What is it?
Beginning.
Okay, let's take it from the top. The top one is what? Application 7. HOL 6. Now what's the next one? Assembly language 5. ASMB 5. That's where that's going to come in. Where are we now? ISA, instruction set architecture 3. And what's in between them? At level 4? Operating system, OS level 4. Oh, that was a good question. Do you see, and you see where we are in the levels? And that's coming up later. Any more questions? These are all really good questions. All right. Now, this next one, figure 4.35, is a machine language program to input 2 letters, characters, and to output them in reverse order. Now let me just walk through this one. So the first one, D1 FC15, is a load byte accumulator. Remember, D1 was the load byte? But where is it loading it from? What do you suppose, do you remember what is that FC15? That's the input. So that's taking a letter from the input. Are you with me? And then what's the next instruction? F1. So what does that do it? Storing at what location? 0013. Well, geez, I don't see a 0013. But do you see that that's the next byte after the stop? So there's nothing there. I mean, there's something there. There's some garbage value there. After we store it, it will be there. Is everybody clear? Okay. Now what's the next one? D1 FC15. What's that?
Taking
Another character from the input device. And now we right away just do what?
output that second character.
Output that second character, because we input it from the input device into the accumulator, and the second instruction takes it from where? From the accumulator to the what?
Output.
To the output. Now does everybody see what that did? So you have to, it's all plumbing, you guys. This is just like stuff is just moving. You just have to have a visual model, a mental model of, these are just little storage containers, and stuff is just going from one part to the other part. Yeah.
In the previous example, we did not have to input before we output it.
Yeah, this is a different program. With this program, if the input is UP, the output is PU. If the input is IJ, the output is JI. So we can do whatever. But with the other one, the information was hardwired into the program. I mean, we had the.
Is it necessary to do it this way though, or could you
These
just
are-
have switched the addresses? You know what I mean?
Well, okay, these are nonsense examples. They're just to show us how the machine works, and so it's just a different illustration. Yeah.
How does this work with what we were before, where it's like you load the return, or you load the return address?
Okay, the return address comes with function calls. We're going to learn that a whole lot later. That's way down the road.
Is that related to this at all, though?
No.
Okay.
No. Okay, so then D1 FC15 inputs the second character, F1 FC16 outputs the second character, and then to output the first character, we do D1 0013, so that loads the first character, and then F1 FC16 outputs the first character, and then we stop. Does everybody see how that worked? Now, here again, watch this. What figure is this? 4.35. Watch this, you guys. You're gonna use this. This little lifesaver, help. You go to help, and look at what we have here. Every figure in the book is built into this app. And here, if you do figure 4.35, this is that program we just looked at. And furthermore, there's a little button here called Copy to Object. And when we click this Copy to Object, the code has been modified. See, he's asking us if we want to save these changes, right? So we don't want to save them. So look what happens. Boom. That code has been copied in, that program has been copied in to here. Does everybody see how that worked? Okay. And if we want to, what we can do is we can go to System and clear the memory from what was there from the previous. And we can come up here and do Start Debugging Object. Oh, and by the way, before we do start debugging, by the way, look what else the system did for us. It put our little input characters there for the test. The test, there's a little test run built in and everything. I mean, it's the input is built in for the test runs, like in the book. Okay, so here we go to build, and we do run object, and watch what happens. Oh, we ran it. We ran the object, so up, and there's PU. But here, we can do this. We can do system, clear memory, and so all of our memory has been cleared. And then we can come up here and do build, and we can do start debugging object. And now, look, we can see what each one of these does. There's the D1 FC15. So what does that do? That takes the what from where and puts it where?
Takes the input.
It takes the U, ASCII character U, and puts it in where? In the accumulator. And see, look, there it is, 7.5. That's 7.5 hex. Well, look, if we do 7.5 hex, sure enough, that's the letter U. See, this is the decimal value. See, it shows the hex value and the decimal value, you know, in the little tracer. Does everybody see? So there's the U, and now watch what happens. What was this next one? What was this next F10013? What was that?
Store it.
Store it. Now, where's it going to store it?
In 1.3.
Well, where's 1.3 up here in the memory dump? This is 1.0, 1.1, 1.2. Where's it going to go?
Right after the stop.
Right there. Watch this. Boom. You can see it. They're in memory as we single step through it in machine language. Is that cool? All right. And then what happens? Then what's the next one? This one got the what? It got the P. That must be the 7.0, right? Yep. So there's the P in the accumulator. All right. And now what happens here? So there goes the P, comes to the output, and now what? it loads the set, it loads the U here in the accumulator, decimal value 117, hex value 0075, or actually the hex value for the character is 75, and with store byte to the output device, PU, stop, and we're done. Is that slick? All right, so that was the demo. And now, this, we have time to take a look at just one more machine language program. Oh, by the way, no, before we won't do this today. Now what let's do is, so your homework assignment is to, your homework assignment is similar to figure 4.33, but what you have to do is you have to output the characters of your first name. But there's one thing, super important requirement. You can't just use 2 letters. Like if your last name is Joe, or sorry, if your first name is Joe, J-O-E, you can't abbreviate it J-O. And you have to use at least 3 letters. Do you see what we're saying? Because look, what's going to happen if we wanted to output 3 letters instead of 2 letters? What would we need to do in figure 4.33?
You're going to have to stop or something.
Well, it's going to take it's going to take another what? It's going to take how many more instructions? 2. You're going to have to do another load byte and another store byte. But if you do a load byte and a store byte, where is that going to put your... It's going to push the stop down, which means that those letters that you store at the bottom are pushed down, which means that they're not at the same addresses as they are here. That you have to deal with in machine language. So you're going to have to know how to count how many letters you want to output, then count, and then figure out the address of where they're supposed to be. Does everybody see how to do the homework? Okay, yeah, question?
Yeah, just kind of looking at the outline from the little examiner file.
No. That's a really good question. Okay. Here's what you could do. After you write the ZZ right here, that's the sentinel for the loader. The loader stops here. You can put your name here. What you can do is this. You can put your name here, date, assignment. And you don't have to put anything, there's no / or anything, because the loader's just going to stop right here. It's going to ignore anything down here. So you can put anything here that you want. You can put it there, if you'd like. But we're only going to do, this is probably going to be I think we're going to write one more machine language program after this. These will probably be the only 2 machine language programs you ever write in your whole life. Because nobody programs in machine language anymore. We're just doing this once so that we can understand how the machine works. But look, you guys, the pioneers, the ones who invented the first electronic computers, what did they have to do? They had to do it like this. There was a row of switches, and they had 1 0 0 0 0 0 1, and then boom, put that one at this location in memory. Boom, put that one in this location in memory. So they would load it manually. Boom, boom, and then boom. Okay, now let's run it. Boom, let's set the program counter. Boom, there's a computation. Because in the beginning there were no operating systems, there was no assembly language programming. When they first built the first computer, we didn't have all this higher levels of abstraction. So the very first computers had to be done literally like this. And this is still what has to happen to run a program in a computer. But now we have all of these. We have text editors, we have operating systems, we have all of this stuff to hide this lower level of abstraction. But look, you guys, it's amazing. All of this software, we can beat a Go player, chess champion. We can beat the Go player. And what does that machine do? What are those computers doing? Fetch, decode, increment, execute, repeat. Just billions of times per second. But that's all it's doing. And it's all just in binary. Can you believe it that we can harness that? It's just super fast. But it's not, the computers, that's all they're doing. Fetch, decode, increment, execute, repeat. Just like this. Okay, good deal. See you next time.